So, let us start lecture 38, and the course is on phase diagrams in single component and binary systems. And today's topic will be how to draw isomorphous phase diagram, and in case of binary ideal solution system. Now, we have been going through all the derivations just to understand one thing, how the equilibrium is arrived in a system with multiple phases. And we have seen that the common tangent rule that decides the equilibrium between two phases, but that too at two specific compositions, because along the common tangent the escaping tendencies of all the components in different phases are equal. So, that means they have to be under equilibrium, and we are fixing temperature and pressure. So, that means the system is in total equilibrium. So, now we will start looking at phase diagrams now. Now, isomorphous phase diagram, that is the topic today. Isomorphous phase diagram appears when we have between solid and liquid solution, and so there it evolves, and we are taking binary ideal solution, and where A and B are two metals, let us say. All the parameters which yield ideal solution, all those parameters are also valid here. And remember, every time we are actually trying to make 1 mole of solution. So, every time we are doing, say, X A and X B are basically the number of moles of A and B in such a fashion that these two adds up to 1 mole. So, that is the 1 mole of solution we are trying to do, and temperature and pressure are constant. Pressure is kept as 1 atmosphere, and now what we will be doing at different temperature, keeping the pressure constant, we will try to look at the equilibrium between two phases, that is solid solution and liquid solutions, fine. And A and B, these are the two metals. So, their melting points are TMA and another melting point is TMB. These are the melting points of A and B, and this is the relation between the melting points and A and B. So, B melting point is higher than A melting point, and here we will be considering, we will be assigning reference value to the pure free energy of A and B depending on the stable condition at that temperature for pure A solid or pure B solid or pure B liquid or pure A liquid. So, we have seen before how to assign the reference value, which is 0 value for those standard quantities, because we are considering 1 atmosphere and that too for the pure substance, and accordingly there will be change in the free energy curves for the solutions, whether solid or liquid solutions, anything if you consider any solution you consider, accordingly it will get changed. Now, let us take, and also let me just draw this particular plot that will be taken as a reference. So, this is temperature, this is G for the pure substance, this is for B case, this is G B naught for solid, and this is G B naught for liquid. And if I try to plot, remember this is a kind of arbitrary plot just to show the variation of free energy values of A and B. Had we known the actual Cp values of liquid and solid A and B, then definitely we would have drawn the actual true scale picture. So, this is a kind of schematic representation. So, this is my TMA and this is TmB, since free energies of solid and liquid for A and B are equal at that junction point. Now, we have to take 5 temperatures. So, those 5 temperatures are, so one temperature is this one, another one is at, this is T1, another one is at TmA. We are taking another temperature as in between TmA and TmB, which is T2, and fourth temperature is TmB, and the fifth temperature is T3. So, that 3 temperature, this all 5 temperatures, we would like to see the plot of G2 for solid solution and liquid solution. And since it is a binary ideal solution, so we have to think a random solution over the entire composition range for the binary system, starting from xb equal to 0 to xb equal to 1. Now, let us start with T1. So, at T1, by using the stability or the free energy hierarchy, I see that Ga naught solid can be taken as 0. Accordingly, I would see the position of Ga naught liquid, and similarly Gb naught solid will be also taken as 0, and here T1, since it is less than TmA. Now, if I try to look at the free energy plot G versus X plot. So, extreme ends are nothing but pure A, this is pure A and this is, or we can write this way, Xa equal to 1, Xb equal to 1, and these 2 points are 0 points. So, this point reflects delta G naught B solid and here Ga naught solid, and correspondingly I can place my liquid free energies of A and B. So, this is liquid free energies, these two. So, I can put it here, this is G B naught liquid and here Ga naught liquid. And whether I am taking solid solution or liquid solution, the equation, governing equation will remain same, G2 equal to G1 plus delta G mix, where G2 is the solution free energy, G1 is the unmixed condition for A and B, and delta G mix is the mixing free energy. Now, this delta G mix will not change for whether we are considering solid solution or liquid solution over the entire composition range, because this delta G mix at a particular temperature can be written as RT Xa ln Xa plus Xp ln Xp. If I take T1 to be fixed, pressure is already 1 atmosphere. Delta G, if I try to draw the delta G mix, so let us say this is my delta G mix. Okay. That is same for both solid solution and liquid solutions. And G1 line, this is my G1 line, let me draw it with a dotted one. This is G1 liquid unmixed and this is my G1 solid unmixed. So, now with that G1 at different compositions, I have to keep adding up delta G mix, which is same for both solid and liquid solutions. Then I can get the G2 for liquid as well as G2 for solid, which is a solution free energy. So, let me draw for liquid solution. So, the liquid solution would be like this. It will be little asymmetric. Why? Because I see that GB liquid, GB naught liquid as GA naught liquid are not on the same line actually, are not same. So, they are different, okay, and that is coming because this gap is little more than this gap. So, that is where it will shift little bit towards, that peak point will come towards on the left for the liquid. So, GT, this is G2 liquid. Now, if I try to draw G2 solid, so G2 solid will fall exactly over delta G mix. This is falling exactly on delta G mix. So, I just let me do it very close to it. I am drawing another curve. Please understand that this is actually falling on the same delta G mix. Now, with this condition, this is G2 solid. So, now you see that at all compositions XB less than equal to 0, 2 less than equal to 1 over this entire composition, okay, I see that G2 solid is less than G2 liquid. So, that hierarchy suggests me that solid will be stable at all compositions. And remember, at XB equal to 1 and XA equal to 1, G2 line would be merging with G1 line, because delta G mix will be 0 there. So, it suggests that over the entire composition, solid solution will be stable. Okay. Now, let us take temperature at T equal to TMA. If I take that, the similar fashion I can go ahead. I can take another plot like this. So, this should be now at this point GA naught solid equal to G liquid should be taken as 0 and GB naught solid to be taken as 0, because at TMA solid B is stable and solid A and liquid A both are in equilibrium. So, this is X and remember this is XB. So, this is XB moving this way. So, this one is both are at the same point, which is 0, and here it will be GB naught solid. So, this is 0 value, okay. And delta G mix, let me not draw delta G mix anymore, because we know that that is same for both. So, we will only see the variation of G2, and this should be GB liquid. Now, I have to see how the liquid G1 before mixing is positioned in this particular plot. So, this is G, this is G free energy, and this is composition, x axis is composition. So, this would be the line, this is G1 liquid, and this should be the G1 solid, which is the 0 0, that is 0 line actually, the line at 0 0 points, XB equal to, and here it is XB equal to 1 and here XA equal to 1. Now, if I draw the free energy line, this will be my G2 liquid, and G2 solid, you will see that G2 solid would be, okay. So, this is G2 solid and this is G1 liquid, and interestingly you will see that since we know that G2 solid at XA equal to 1 is equal to G1 of solid at the same composition equal to G2 liquid at XA equal to 1. Fine. So, only at, or we can say XB equal to 0 or XB equal to 0. So, except XB equal to 0. So, that means if I try to see the composition pattern, so this is XB equal to 1 greater than and XB, this composition range, I see that G2 solid is less than G2 liquid. Okay. So, it suggests that in this case, apart from XA equal to 1 or the pure A point or A composition, pure A composition, so all those cases solid solution will be stable. Okay. When we try to look at this, at this point XP equal to, so this point I see that solid as well as liquid, they will be under equilibrium. Hence, solid and liquid both coexist. So, that means I can say that the first liquid will start appearing, because if I see at T1 and if I compare with T equal to TMA, I see that at one point only the free energy of solid solution and liquid solution, which is nothing but the pure A, are merging each other. So, that means initially everything was solid at T1. So, now as we increase the temperature, we see that the first liquid will start appearing in the system is at composition Xa equal to 1. So, if I try to plot these two over temperature and composition plot, okay, which is nothing but the phase diagram axis. So, if I try to plot that, so let me plot it here. So, here if I try to plot, so this is X B and we have taken a temperature T1 and this is temperature axis. So, T1 everything was solid. Now, we have come to TMA. So, there at this location, I will see appearance of liquid. Okay. Here everything would be solid. Now, I could see that on a particular temperature composition plot, I can see the stability of solid and liquid over the entire composition range at these two temperatures. Let me just extend our discussion over 3 other temperatures. So, another temperature, this particular temperature would be little critical temperature. So, that is what that T2. So, we will not consider T2 first, we will consider T3 and then we will come to TMB. Okay. Let us take that two situations. So, we are taking situation here. So, now we are trying to draw at T3 and we are trying to draw at TMB the free energy of solid and liquid. Okay. So, if I try to draw for T equal to T3, that means at that particular case I will see that you just match with this particular G versus T plot for A and B. I will see that G or GA liquid should be considered as 0 reference point, and G B not liquid should also be taken as 0, because at T3 which is greater than TMB, both A and B in pure condition should remain liquid. Okay, that is the stable form. So, that is what we are taking 0 0 there. So, now if we try to draw that, this is x b equal to 1, this is x a equal to 1, and also this value is 0 here. So, this particular 0 point is nothing but G naught B liquid, and here it is G A naught liquid, and correspondingly I have to put those points for solid and liquid for pure A and pure B. Solid for pure A and pure B, this is not G A solid, and let us say this is my G naught B solid at T3. So, now I can draw those two G2 lines. So, here it is, this is G1 solid and this would be G1 liquid. Now, if I draw that liquid line, this one, and solid line would be this one. So, this is G2 solid and this one is G2 liquid. So, I see that composition range XB less than equal to 1 greater than equal to 0, G2 liquid is less than G2 solid. It suggests that liquid solution will be stable over the entire composition range. So, if I try to plot it over this particular case, so I can draw T3 here, this is let us say T3. So, I see all the places it would be liquid solution. Now, at TMB, let us look at TMB at T equal to TMB. If I look at those free energy plots for pure metals, then I can take G A naught liquid should be 0 and G B naught solid equal to G B naught liquid equal to 0, because at TMB free energies for B for solid and liquid both are equal. So, that is what that reference value should be taken as 0. And remember, every time this naught suggests that it is a standard state, because pressure we have taken 1 atmosphere. So, if I try to plot that, I will see that the plot pattern would look like this. This would be x b equal to 1, x b x a equal to 1, and this is x b, and of course, remember that this composition variation is this way and this is G varying like this, and let me see whether I have put all those mark. Yes. Now, this would be G B naught solid equal to G B naught liquid equal to 0. So, this is 0 point, and here G A naught liquid should be taken as 0 point. So, this is 0 point, and correspondingly this would be my G A naught solid. So, if I try to see the G1 for the unmixed condition, G1 for solid and liquid, So, this becomes my G1 solid and this is my G1 liquid. So, if I plot solid G2 and liquid G2, so this would be my this is G2 solid and G2 liquid would be okay. So, this is G2 liquid. Now, let us see at composition at XB equal to 1, I see that G2 liquid equal to G2 solid. So, similar logic, whatever logic we have put here under this condition, you can extend that logic with respect to B to this. So, at TMB, I will see that solid and liquid, of course, for the B pure B phase and the previous case it was pure A case. So, this is pure B and here it was for pure A, pure B coexist. That means, if I start from a higher temperature and slowly temperature is dropped to TMB, the first solid will start appearing, because very high temperature which is T3, everything was solid liquid solution. Now, as we come down with that on the temperature axis, I see that the first solid would appear in case of pure B. While I started from a lowest temperature which is T1, I will see the first liquid will start appearing at TMA with the pure A side as we increase the temperature. So, here first solid will appear, of course, with respect to pure B, first solid will appear at temperature TMB. In case of cases where I have started at a lowest temperature to as we go to TMA, the first liquid started appearing in at XA equal to 1. So, other compositions XB less than 1, 0, G2 liquid is less than G2 solid. So, that free energy hierarchy. So, it suggests that will be stable over the entire composition except XB equal to 1. So, if I try to plot the same thing on this particular T versus XB plot, so at this location I will see that the first solid B will start appearing if I go down like this, and in this case here I see first liquid started appearing at XA equal to 1. So, we have seen two extreme points, one point is this, one point is this. Now, our calculation, our understanding will have to be considered when I am considering a temperature which is in between, which is T2. So, the T2 point becomes very important aspect. So, now we see that at T2 we have to consider how those phases will appear, what will be the composition of liquid as well as what will be the composition of solid. And at T2 we will see that this G2 line for solid and liquid solution will cross each other, and due to that crossover, in order to find equilibrium we have to bring in the common tangent rule, and that common tangent rule will tell us what two compositions will be under equilibrium, and those two compositions correspond to solid solution as well as liquid solution. So, I will talk about that particular free energy situation as well as common tangent rule to decide the equilibrium between the two phases in the situation where pressure is constant and T2 temperature is kept constant at T2. So, that we will take up in the next class. So, till then, thank you very much.